Welcome back, everybody. Is everybody here today? 2, 4, 6, 8, 10, 12. Everybody's here. Um, Coffee's back. Coming back. We didn't do anything yesterday. We just waited for you to come back.
Aw, how nice.
Horseshoe.
I'm not gonna cap. I did not watch the video.
It was a word.
I thought it was a word.
Yeah, that would have been good if you got it. Check it out.
Oh, I watched the video.
Of course I did. All right. So, yeah, again, we're right here. We're making it through the difficult part of the year. So this is good. We're just hop, skip, and a jump away from Thanksgiving. No, I'm talking about like in terms of like the day, long weeks with no days off. There's only one stretch in there that's 3 weeks full with no days off. That's right before Thanksgiving. But we're right here. We're there, folks. We're there. All right. So this is section 2.8, derivative as a function. It's funny. I was rewatching the video from last year to kind of like refresh my memory just to see. I do that every because I have third period planning. I watched the video that I did last year just to see if I like want to teach it better or what I did last year. And you know what's funny? One of my kids referenced last year. They were like, "Why is vertical written on the board?" And it is this year too.
Oh my!
Isn't that crazy?
That is cool.
That's so weird. Somebody last year said, "Why is vertical written on the board?" Because my very intelligent Algebra 1 students spell it like this. This is incorrect. Hence the front of it. This is the correct version of the vertical. Right, yes. Okay. But I just thought that was like really odd. Like, what's that? Horizontal. TLE. Well, that would be weird. Hopefully they recognize that is weird. All right. So what we're going to talk about today is the derivative as a function. What is the derivative? Well, the derivative is the slope, right? Derivative is equivalent to slope, right? That's what we learned in section 2.7. If you learned anything about a derivative, I hope you think of derivative as a slope. Derivative is equal to a slope. Where? At any given a value, right? That's what we learned last section. F prime of a, where a is any x value that I choose, is equivalent to f of a plus h minus f of a all over h, and the limit as h goes to 0 of that thing, right? This is technically the slope, f of x minus f of a over x minus a, right? It's just a manipulation of that equation. So what if we generalized it? What if we said a is no longer just some singular number on the graph? What if a was any point on the graph? What if we could come up with an equation that if we plugged in the x value, it would give me out the slope at that point? That's what we're looking at today. Defining derivative as a function. So what we're looking at today, again, let me repeat that. I'm going to be giving us equations. We're going to be giving us functions, both graphically and as the equation. And we're going to be looking at that equation and saying, okay, what is the derivative? Meaning, at any point on the graph, what is the slope? What is the slope? And instead of just picking out 1, 2 singular pieces of the graph, what we're going to say is, okay, can we generalize that function so that we can create an equation so that the output is the slope? And we can, and it's that's like what the whole next chapter is about as well. Finding the derivatives as functions, not just a single value as a function. So what we do is we just change the notation a little bit. What's the difference in notation? This is f prime of x. Oops. Go back. This is f prime of x is really just equivalent to x plus h minus f of x all over h. F of x plus h instead of f of a plus h. It's really the same thing. But when you're calling it a function, all you need to do is just plug in x instead of a. If you want to find the slope at any given point, you plug in that value for x, which we called a before. So it's really just a change of notation, just leaving the x in there at any given time. Okay. Given any number for x for which the limit exists, we assign x to the number f prime of x So f prime is a new function. It's a new function that the output of that function is going to give us the slope at any given time of x. So notice that the input value didn't change. The input is still x. You know, x is x, no matter whether we're talking about the regular function or its derivative. X is x. The output is changing. Okay? If I'm talking about the original function, the output is the y value of the function. But if I talk about its derivative, I'm going to say inputting x will give me the slope of the original at that point. Okay? All right, so let's take a look here and try to represent it graphically. This is a very difficult task. It's extremely difficult to look at a function and to graph its derivative just by the look of the function. That is a very hard thing to do. And we will do this a lot later on as well. So this is just an introduction into how we visualize a derivative, because that's really a lot of calculus. Can you visualize based on only certain information? That's why that activity that we did where we were voicing our graph to the other person, that's why that's so difficult. That's why it's so important to do. All right, so here's my function. I'm not even given an equation. This is just a graph function, weird looking function that we have. Let's try to graph its derivative. Well, to graph the derivative, let me get some. Let me get an axis on here. Okay. Now, my input is input, right? That's not going to change. But now, what is my output? For the derivative, if I'm graphing the derivative, the x value is the x value, but the output of the derivative is what? The slope. So it's not x comma y, it's x comma m, where m is the slope. So let's take a look at this function and see if we can pick out certain pieces where I can define the slope. Like, for example, take a look at some critical points of this graph. That's a term that you're going to hear me say a lot. Take a look at some critical points of the graph. Think about the slope of the tangent line at any one of those points that I just put on there. If I took a pencil, black tack on the rubber. If I took a pencil and I wanted to trace along the slope, and this pencil was representing the slope, what would the slope be at that point? 0. Because it would be going down, 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 right there. And then at that point, the slope would be going from this up. I should really do this on the TV so it doesn't start wrong. Right? I can put it right on. See, the slope is going to go downward, 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 and then level out right there, isn't it? And then at that point, it's going to start going up. And then here, it's going to level out again, isn't it? And then here, it's going to go down the line and then level out here. So what's happening at each one of those critical points? What's the slope? 0. So at x equals, that looks like about 0.5. The x equals 0.5, at x equals 1.5, and at x equals 3, I have these coordinates where if the input is 0.5, 1.5, or 3, the output is 0. They're actually zeros of the function. They're the zeros of the derivative. So let's put on here 1, 2, 3, 4, 5, just like I have in my original. 1, 2, 3, 4, 5. At x equals 0.5, the slope is 0. At x equals 1.5, the slope is 0. At x equals 3, the slope is 0. Okay, well, let's bring our pencil back. Okay, so what's happening to the left of 0.5? What is the slope to the left of 0.5? Positive or negative? Negative slope. And it's negative, 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 negative. And then what happens between 0.5 and 1.5? it turns positive slope, right? Okay, well, how do we represent that then? Well, the slope is negative. So it's below the x-axis. Then it turns positive. The slope is positive. Then it goes back negative. And it goes pretty steeply negative, doesn't it? So this is a pretty big negative slope. Down, 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 roller coaster, then levels back out again, right? So the slope is pretty steep in the negative direction. So the slope is negative between 1.5 and 3, and it's a pretty steep line. It's pretty high value. So let's make it dive down a little bit more into the negatives than I went into the positives. Okay. And then what happens to the right of 3? The slope turns back positive and only keeps getting bigger and bigger and bigger, right? So I can keep making it go. Oh, sorry, that should have been a nice smooth line. Sorry about that. You kind of get the idea. But it's going into the positive directions. So what we're looking at here is everywhere where the slope of the tangent line is negative, you're going to see it as below the x-axis on its derivative. Anywhere where the slope levels out, you're going to see a 0. Anywhere where the slope is positive, it's going to be above the x-axis. Okay? So that's where we can try to start graphing. Now, beyond that, it's just an estimation. Like, okay, what is the actual slope at those given points? Well, then we just kind of got to sketch that a little bit. But the critical points here are where the slope turns from positive to negative and where it levels out at 0. Because and we'll actually talk about these, I think, once we get past like all the rules about derivatives, I think in chapter 4 in the second semester, we actually talk about, okay, well, then that means that any maximum or minimum point that we have is a 0 of the derivative, which then we can start saying, okay, if the zeros of the function, or sorry, excuse me, if the maximum or minimum values of the function are the zeros of the derivative, well, then what's going on here? Like, what are the maximum minimum values of the derivative? What does that imply? Then we start learning about that. But again, that's a little foreshadowing. Okay. So now let's take a function, an actual equation. Let's take an actual equation and find the derivative of it. I'll tell you this quiz that we got next week, that next Thursday, I think I said it was, it's a lot like a bunch of part A's. No, it's a bunch of part A's here. All right, we got x to the third minus x. Find the formula for f prime of x. Okay, so f prime of x is the limit as h goes to 0 of f of x plus h minus f of x. Forget the formula. F of x? Yeah, f of x. All over h. You want to know something like really sad? Not really sad. Really something to look forward to. Yeah. In chapter 3, by like section 3.2, you're going to be able to calculate this derivative in like a second. And that's not an exaggeration. But for right now, we got to do the hard work. We got to do the dirty work. All right, so now let's find f of x plus h. X plus h goes in for x. Okay. X plus h to the third minus x plus h. And then minus f of x. Minus x to the third minus x. All divided by h. Does everybody follow me what I did? All I did was plug in x plus h into here and here. And then just subtract away f of x. Now can I evaluate using direct substitution? Again, you're seeing a theme here. So we have to algebraically manipulate it. Let's take x plus h to the third and just simplify that for a second. Because remember, that's this. I die a little inside. Everybody tries to just like distribute that third to the inside of the parentheses, like x to the third plus h to the third. Okay, so let's FOIL this. So that's x plus h times x squared. Then we got xh and xh. So plus 2xh plus h squared. Do I have to write your path?
What?
Do I have to write your path? Where are you going?
Mark.
Okay, you're good. So now I'm going to multiply in the x and then the h. So this is, we've got x to the third plus 2x squared h plus xh squared. And then multiply in the h plus x squared h plus 2xh squared plus h to the third. This is just FOILing this all out, basically. And I combine like terms. I've got an x to the third. I've got an x squared h and an x squared h. So that's plus 3x squared h. Xh squared and a 2xh squared. So plus 3xh squared plus h to the third. You know what we could have used here? Pascal's triangle, if we would want it to. Remember that?
No.
Yeah, that's a throwback. All right, so all this was just x to the third, x plus h to the third. So this is x to the third plus 3x squared h plus 3xh squared plus h to the third. And now we have this minus x minus h. Then this minus x to the third plus x. Remember, I'm distributing in the negative there. All divided by h. Now, let's hope and pray that a lot of stuff cancels. Okay, we've got x to the third and a negative x to the third. We've got a negative x and a positive x. Oh, no. That's it, isn't it? That's fine. That's okay. Because now this is a 3x squared h plus 3xh squared plus h to the third minus h, all divided by h. Now, what can I do with my h's? Cancel them all out, right? Well, not all of them. But like this cancels here, cancels one of them here, cancels to be a 2 there, and cancels it there. And now I'm going to bring my limit back in. Because that was the end goal, right? The limit as x goes to, excuse me, the limit as h goes to 0 of 3x squared plus 3xh plus h squared minus 1. Remember, that's a 1 right here. H divided by h, that's a 1. Be careful with that. That doesn't just go away. So if I'm evaluating the limit, now can I do direct substitution? Yes. Let's plug in 0 for h. 3x squared stays 3x squared plus 3 times x times 0 plus 0 squared minus 1. Oh, so long, farewell. We got 3x squared minus 1. That's the derivative. F prime of x is 3x squared minus 1. That's the derivative. Again, I say to you, when we get to chapter 3, you will literally be able to do that in like 2 seconds. Is it upsetting or make you hopeful?
It's annoying now, but
It's, yeah.
later.
Now, part B says let's look at the graphs of f and f prime and just see what's happening. Let's just see what's going on. So here's f, x to the third minus x. Here's f prime. Look, I don't even need to look down there. I know that it's 3x squared minus 1. Let's turn off this one first, though. I'm going to do this. I'm going to graph zoom 6. I'm going to graph this one here. This is my original. And then this is my derivative. Turn off, turn on. Okay, so let's see if what we did on the first slide relates to anything that we did on the second slide here. I'm going to go back to the TV so I can actually put my pencil on it. Okay, look. Now, you don't really see it very much, but it does go up and over. Okay, if I zoomed in a little bit, it does go up and over the graph and kind of like curve like that. What's the slope? Positive. Positive, 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 levels out, goes back down, levels out, positive, right? So it's positive, positive. Now, it's above the x-axis. It's above the x-axis. It's below the x-axis. It's above the x-axis. Where is it going through the x-axis? There and there. The maximum and minimum values of the function are the zeros of the derivative. Okay? Now, this is more for later. Right? We're going to get into this a lot later in chapter 4. This is what we should be really focusing on right now, the whole algebraic piece of it. Okay? Let's do another one. I was looking down, looking, I was like expected it to be like 10:50. Man, we got plenty of time. We got 25 minutes left class. Woo! We need more time to have fun.
Fun Friday.
This is just awesome. I love this stuff. Honestly, this is where it starts to get really fun for me because it's a lot of algebraic work.
I like that.
You like that?
Yeah.
Okay, f of x is equal to the square root of x. Find the derivative of f and then state the domain of f prime. All right, so f prime, remember f prime, our formula for f prime is the limit, write that first, the limit as h goes to 0 of f of x plus h, come on now, f of x plus h minus f of x all over h. Okay, so let's plug in x plus h, put it in the numerator. Minus f of x, which is just the square root of x, all divided by h. So hopefully this one's a little bit easier to reduce down. The complexity of finding the derivative really comes with the complexity of the original function. Okay? The more complex the original function, the more complex it is to find the derivative of it. Now, we're still finding the limit as h goes to 0 of this thing, right? Square root of x plus h minus square root of x all over h. Can I directly substitute? No. So I'm going to need to do something to get h out of the denominator. You want to know what that thing is? It's that whole multiplying by the conjugate thing. Okay? Whenever you see a square root, usually that whole conjugate thing is going to help us. All right, so let's multiply. My first, square root of x plus h times the square root of x plus h is just x plus h. Now, what happens with my inners and outers? Cancel. Inners is negative radical x times radical x plus h. Outers is positive radical x times radical x plus h. So the inners and outers will cancel, and then will leave me with this. Negative radical x times positive radical x. It's just minus x. All over. Now, be careful, because I had some people on the quiz to write just an h on the bottom. Be careful with that. It's h times all of that. H times radical x plus h plus radical x. That's an x. Okay, look at our numerator there. The x's, oh, that's yellow. Okay. The x's cancel, leaving us an h over h radical x plus h plus radical x. Now my h's can cancel. Now we take those h's away, which leaves me with a 1 over square root of x plus h plus the square root of x. And again, that's the limit as h goes to 0. Now can I directly substitute? Yes. Now I can. Now I can say this is going to be 1 over the square root of x plus 0 plus the square root of x. All right, so that's 1 over square root of x plus square root of x. So 1 over 2 square root of x. And I should write it using the notation f prime of x is equal to 1 over 2 radical x. Again, once we get to section, I think that's probably a little bit later on in the chapter, but once we get to section like 3.3 or so, 3.4, you're going to be able to do that one a lot quicker than what we just did. But it's good to know the background, good to know where it comes from. Okay? Questions about that one? Let's do another one. Okay, f prime, we're finding f prime with f of x is equal to, oh, you know what I forgot to do? We didn't talk about the domain. State the domain. Because there's one thing that I have to say about the domain. The domain of f. What was the original domain of f? X is greater than or equal to 0, right? Can I still have that same domain? My domain was all x values greater than or equal to 0. Can I still have that domain? I just have to change one thing. Just greater than. It can't be 0 anymore. Now, why do we talk about that? Why is that unique? Well, I'll tell you this. When you're talking about the original and the derivative, the derivative's domain is never bigger than the original's domain. Okay? The derivative's domain is never bigger than the original's domain. It could be smaller, it could be the same, but it could never be bigger than the original's domain. Like, if the original domain was x is greater than or equal to 0, the derivatives can't be all real numbers. You have to start with the restriction on the domain of f, and then it's only going to get smaller. Just a little bit smaller, just not including 0 this time. All right, let's take a look at this one. We got 1 minus x over 2 plus x. This one's a doozy. This one's a fun one. Ooh. Okay. So find f prime. So f prime of x, again, is equal to the limit. As h goes to 0, you're going to see me write this every time because it's good to memorize. X plus h minus f of x all over h. Okay, so my first step is to plug in x plus h. So this is 1 minus x plus h over 2 plus x plus h. Right? That's just f of x plus h. Make sure whenever you put a minus sign in front of it, you've got to put it in parentheses or you're going to screw it up. You're going to forget to distribute in the negative. Okay? Be very careful with negatives like that. Okay, minus f of x. So the original function, 1 minus x over 2 plus x, all divided by h. So this is just a nasty, complex rational function. I've got fractions within fractions, right? And again, I can't directly substitute because I've got h going to 0. So I've got to do some manipulation. So here's what I'm going to do. I'm going to take only the numerator. And I'm going to reduce down the numerator. Okay? The numerator was 1 minus x plus h over 2 plus x plus h minus 1 over x, or sorry, excuse me, minus 1 minus x over 2 plus x. Let's first kind of get these parentheses to go away on the left side. So 1 minus x minus h. I guess that's the only thing that I'm changing. Okay. All right. That wasn't that big of a change. Okay, now I have to get common denominators. All right. So my LCD, I have to multiply this one by 2 plus x over 2 plus x. I have to multiply this one by this guy's denominator, 2 plus x plus h over 2 plus x plus h. Okay? I'm just multiplying by the other's denominator. I'm multiplying this one by 2 plus x, top to bottom. I'm multiplying this one by 2 plus x plus h because that was the other guy's denominator. So in the end, it's going to get me this as my common denominators. 2 plus x plus h times 2 plus x. Equals something, 2 plus x plus h, 2 plus x. Okay, now this is going to be some multiplication here. All right, let's distribute it. Let's actually multiply these things together. Okay. So this is, and I'm going to do the work right above it here. 2 times 1 is 2, minus 2x, minus 2h. Here, this is going to be bringing in the x. X minus x squared minus xh. To reduce down to, looks like I've got, let's pull the x squared all the way out front. X squared. Looks like I've got a minus 1x, and looks like minus 2h. Okay, we've got to keep track. Here, got those out of the way. Minus 2h, minus xh, plus 2. Okay, and the numerators here, this is going to be 1 times 2. Again, I'm multiplying this and this together. I've got 1 times this whole thing, so 2 plus x plus h. And then minus 2x minus x squared minus xh. Okay, that's all just in the numerator here, just as multiplying those two things. All right, so that let's reduce it down. We got a minus x squared. That takes that out of the picture. And then we've got, okay, that'll cancel. That's nice. Ooh, that'll cancel. No, that's a lie. That won't cancel. I just did something I shouldn't have. There we go. That's x plus h. So we got minus x squared. I've got a minus x with this. Minus xh plus h plus 2. This is nasty. Okay, let's distribute in this negative now. Okay. You know it, brother. I'm sorry, I just made a mistake there. Hold on a second. because I was looking at my key here. That should be a negative x squared. I copied that down wrong. Okay. I knew that because these are going to cancel. Look, watch. Negative x squared minus a negative x squared. Aren't those going to cancel? Negative 1x and a negative 1x. Aren't those going to cancel? Negative xh and a negative xh. Aren't those going to cancel? Positive 2 and a positive 2. Aren't those going to cancel? So leaving us with a plus h over here and a negative 2h. So negative 2h minus h. Negative 3h. Because again, this is minus. This is minus, not plus. Negative 2h minus h, so negative 3h. Okay, so let's find the limit as h goes to 0 of this whole thing. Oh, that's still just the numerator. Thank you for a second, because I just saw that there. I was like, wait a sec, that h should cancel. Because look, this is all the numerator, and then I'm dividing by h, right? Or in other words, multiplying by 1 over h. I was going to say, like, that h should not be there, because it should cancel like that. Leaving us with negative 3 over 2 plus x plus h times 2 plus x. Now, I don't have to FOIL that out because I am going to evaluate the limit as h goes to 0 of this thing. Which is negative 3 over 2 plus x times 2 plus x. Right? Because that h goes away because we put it to 0. We directly substitute it in. So in other words, that would be fine if I wanted to leave it like that. Negative 3 over x plus h squared. That's the derivative. Woo! That was fun. Ladies and gentlemen, that was an awesome problem. Can I tell you something? Let's remember this feeling right now of how difficult that problem is. Because when we learn what's called the quotient rule in chapter 3, you're still going to think that's difficult. You're still going to think the quotient rule for a rational function is difficult. But remind yourselves, like let's say in the recording, that was really hard. Okay? Appreciate the dang rule, kids, in the future. Okay. Yes?
Is that supposed to be an x plus 2 and an x plus h?
Oh! Sorry, that's a 2. That's a 2. 2's h, whatever, you know. But again, appreciate the dang rule, kids. Well, I'm going to replay this for you guys when we learn this. Just that clip. Okay. Let's stop for today. That was a good day.